I'm not sure if anyone is able to hear me. Let's see. Okay, very good. Yeah, thank you for letting me know. Okay. Let's see if this works. Okay. All right. I wasn't feeling very well, so I think we'll keep this a short lecture. I'm winding up. I just want to wind up some of the material. Excuse me. From the last lecture, just finish it up because we had the pre-test and that took away some of our time. So I just want to finish this up and we'll get through this lecture, and then the next lecture will be switching over to linear algebra. So, all right. So for today's lecture is pretty short. I think we'll be talking about single qubit gates and quantum circuits. So the definition of a quantum gate, specifically a single qubit gate, is that a quantum gate transforms qubit states into other states. And so quantum gates are specifically, though, they're not just any transformation. We can't just transform one qubit state into another qubit state with no restrictions. We have two important restrictions. The first one is that it is, let me just see. That it's linear, okay? And the second is that the total probability must be equal to 1. So we denote quantum gates by the symbol U. So here's an example of a transformation that we are considering. So it's a map, as I said. So a map basically takes the state 0 into this other state. And similarly, it takes the state 1 into this other state. Now we have to verify two things, as I just mentioned. We have to verify that it's linear, and we have to verify that it, we define that it has to be linear, but now we need to verify that it actually keeps the state probabilities equal to 1. So to do that, I take U and I act it on any general state, A0 plus B1. And the assumption is that A and B are normal. That state is a valid qubit state. So A squared plus B squared equals 1. And now we need to show that this U acting on this state keeps it as a normalized state. Sorry, my iPad is a bit sensitive, I guess. All right, so because it's a linear state, we can just take the U inside and act on the state 0, and similarly on the state 1, because A and B are just constant, some arbitrary constants for this given qubit state psi. So this is the state, any general state psi of the qubit. Okay, and now we just need to carry out the transformation. So we have A with U acting on 0. Let me just stop or hide this panel here.
Should have read that, but I did not.
Does somebody have a question? Okay. If you have a question, just speak up or raise your hand in the chat. Okay. So U acting on 0 is root 2 minus I by 2 acting on 0 minus 1/2 acting on 1. And similarly, this is B times half state 0 root 2 minus I divided by 2 state 1. And now we need to verify that this is normalized. So to do that, we'll collect all the terms that have the state 0 and all the terms that have state 1, and that'll be our new coefficients A1 and B1 for this new state. So let's just do that. It's a little bit of algebra, but not difficult. Times A plus 1/2 B. This is what is now the coefficient of the 0 state. And similarly, for the 1 state, we have minus 1/2 A plus B times square root 2 minus I divided by 2. And all of this is now the coefficient of state 1. Right? We just follow the algebra over there. Okay. Maybe I should change my pen color if I can. I guess I can't. Okay. Here. Is this any better? Yeah, that's a little better. Okay. Let's add in extra slide here so that I can let's see. There's no easy way to do that, is there? Okay, so I'll insert a blank slide. And let's see. Just blank. Okay. No. Okay. Okay, so we have these two coefficients. We have this coefficient A1 and this coefficient B1. So let me make sure I have to transfer it over from one side to the other. So A1 equals root 2 minus I divided by 2 times A plus half times B, and B1 equals minus 1/2 A plus B times root 2 minus I divided by 2. So now we need to calculate norm of A1 squared, which is just taken by finding root 2 minus I divided by 2 times A plus 1/2 B, multiplying that by its complex conjugate. So that is root 2 plus I divided by 2 times A star plus 1/2 B star. And similarly, modulo B1 squared, the coefficient in front of 1, is minus 1/2 A plus B times square root 2 minus I by 2. And then over here, this is minus 1/2 A star plus B star root 2 plus I divided by 2. Okay, so we need to calculate each of these and then add them together and show that that is still 1. Okay, so, I'll carry out the multiplication. I take all the cross terms and multiply out. So the first term is 4 plus 1 divided by 2, because that's just root 2 minus I norm squared. So that's 5 over 2 times A squared. No, 5 over 4, sorry. Plus B squared divided by 4. once again, I managed to screw up my norm squared. So I don't know. Let me know if this green is worse or better. So that's 2 plus 1, not 4 plus 1. So that's 3 over 4 here. And then we have the cross terms, which are going to be root 2 minus I divided by 2 times divided by 4 actually, times A B star plus root 2 plus I divided by 4 A star B. Similarly, we can work out B1 squared, and that is going to be 1/4 A squared plus now this cross product plus the square. That term is going to be now again similarly 3/4 of B squared. And now we have to hope that all the cross terms disappear. If I did everything correctly, minus 1/4 of root 2 plus I times A B star from the first term multiplying that second term there. And this one is root 2 minus I divided by 4 times B A star. Yes. So we see that the terms all cancel. And we get with, so we end up with this whole thing adding up A1 squared plus B1 squared is equal to A squared plus B squared, which is equal to 1. Okay. All right. Hopefully that's clear to everyone. So I'll proceed unless you have a question there. Okay. I'm not hearing any questions. So let us now talk about what types of gates are valid quantum gates. And the main the first types of gates that we can immediately write down as classical as valid quantum gates are classical reversible gates. So all of the digital binary gates that we discussed in the first couple weeks of this class, we said that classical reversible gates, which weren't very useful in classical computing, but they preserve all the information. And that is very useful for quantum computing because what they do is simply shuffle the input bits around in the output. So as an example, this is the simplest example, obviously, is if you take the gate, that is the NOT gate. So this is the NOT gate. And what it does is it takes A to 1, 0 to 1 and 1 to 0. So in any quantum state, if I take the 0 state to the 1 state and the 1 state to the 0 state, I've simply permuted the state around, but I haven't changed its normalization. So that's important. And also it's going to be linear because of that. So as a simple example, this has a special name. This NOT gate has a special name in quantum computing. That is, it's called the Pauli X gate. And you'll see why in just a minute. But just to carry out this classical reversible gate acting on the state A times 0 plus B times 1, we have to verify that this is indeed now going to preserve the normalization of the state. And so it's very straightforward to see that. So it's A acting on U of 0 plus B acting on U of 1, right? When I take that U inside, and that's just going to give me A acting on 1 plus B acting on 0. And so that's the action of the NOT gate. It flips those 0 and 1 states around. And because this state is, so obviously the normalization of the state doesn't change because it's just still A squared plus B squared. So as long as A squared plus B squared was 1, this state will also remain normalized. So this action of this poly gate, the poly X gate, can be looked at on the block sphere as taking the state 0 and flipping it to the 1. Okay. And also, I should mention there are some other common identity gates. So one is the identity gate I acting on 0 and I acting on 1. This state preserves 0 and 1. So therefore, it must by automatically preserves normalization. Therefore, it is also an allowable gate. And now we come to this poly X gate that I was just talking about. As you can see, it looks like a rotation around the X axis because it takes the point on the North Pole and converts it to the South Pole. So that is corresponding to a 180-degree rotation around the X axis in the block sphere. And obviously, if I repeat that, if I do X and then X again, now I'll take 1 and I'll take it up to 0. So it'll bring me back as an identity gate. And that is verified over here in this next, just showing you that indeed that is exactly what happens. By the way, sorry, if in case it's not clear, these little dots here are meant to indicate the path that it takes, but the final state of the poly X gate is always that final state. These intermediate states are just what I was trying to show you is the path that the block vector will take. The state will take, the qubit state will take as it goes from 1 to 0, but it doesn't say that X will result in each of these states. It doesn't. At the end of the X gate, so to speak, the X gate takes some finite amount of time. It will end up with the state 0 here if you start in the state 1. But of course, every gate takes some finite amount of time. And during that finite time, this is the path, ideal path that a qubit state would take as it goes from 1 to 0. By the way, you can come up with some other gates. For example, if I did the constant gate, which says that 0 goes to 0 and 1 goes to 0, you can immediately see that is not going to be normalized because it's going to take A times 0 plus B times 1 to A plus B times 0, which is no longer guaranteed to be normalized. So that's important to understand. Okay. So only specific gates, which we'll discuss, are going to preserve this normalization. Okay, I told you about the action of X on the 0 state, but it's important, as we've already seen in many of the quantum operations, to know what happens when X acts on other states, not just 0 and 1. And so it's, again, we can verify what happens to the plus state. The plus state is just simply 1 over root 2, 0 plus 1 over root 2, 1. And therefore, as we can see, this is going to be just 1 over root 2, 1 plus 1 over root 2, 0, which therefore is also the plus state. So X acting on the plus state gives me back the plus state. What about X acting on the minus state? Well, again, we flip the 1 and the 0. And now we see that if this is equal to 1 over root 2 of minus 0 or is equal to, sorry, oops, I just wanted to erase that, but okay, this is 0 minus 1, but with a minus sign outside. Okay, minus 1 outside, as you can see from this state. So what this is the state minus of minus. So at first glance, you think that X does not preserve the minus state, but of course, remember, minus sign is just a global phase outside the state, so therefore it is still preserving the minus state effectively, because as we know, minus state is equivalent to minus minus in our convention, because global phases do not matter. Okay. Another way to see that is if I look at a state, a qubit state that say along the minus x-axis, right? That's what the minus state is. Then of course, by rotating it around the x-axis, I should not change it. And indeed, right, because it's along the same axis as the axis of rotation, I mean, it's along the axis of rotation, it will not change. Even though, of course, we add this minus phase to it, which is important because otherwise you wouldn't take 1 back to 0. You can verify for yourself that if you didn't have that, then it wouldn't take 1 back to 0. It would just keep 0 to 1 and it would destroy the 1 state. So that's not a good, valid quantum gate. Okay, I'll let you work out for yourself what x acting on plus I and minus I is. It's very straightforward. It's just exactly the same thing. But now, instead of having 1 over root 2, 0 plus 1 over root 2, 1, you'll need to add the plus I there because that's what plus I is. Over here, you can just put an I there, similarly minus I, and you can verify for yourself that x, and also this is why the intuition is helpful back here. So remember, plus I state will be over here. So obviously, if I rotate by 180 degrees around the x-axis, right, that's going to take plus I to minus I. So we can predict what is going to happen, and then you can verify it with the algebra. Similarly, minus I, if I rotate it again around the x-axis, will get me back to plus I with a possible, of course, global phase, which is why you need to verify what actually happens when you do the algebra, just to make sure that you're getting it correctly. Okay, so here are some other single qubit gates. As you can imagine, once you can have a poly X gate, you can do a poly Y gate. Okay, so that corresponds to a 180-degree rotation around the Y axis in the block sphere. Again, Y squared, again, just like X squared, Y squared must bring me back to the identity matrix, that it does nothing. By the way, I didn't talk about this, but hopefully it's obvious to you that if I can do Y and I know what the action of Y is and I know what the action of Y squared is, I can build up action of any number of Y gates. So Y to the 500 would be just Y squared to the 250, right? And since Y squared is the identity operator, that's just the identity. So, and then of course, Y to the power 501 would be just Y again, because Y to the 500 was identity. Therefore, identity times Y must give me back Y. So just to quickly write that down. So Y to say 500 is just identity, and Y to say 501 will be just Y. So we see that, even number of Y rotations or Y gates will give me identity, odd number will bring me back to Y itself. Okay, and what is Y? In this case, Y, we see that Y takes 0 to 1 with a plus I phase, okay? And it takes Y, the 1 to the minus I times 0. So it flips 0 to 1, and it also has a phase I. So it doesn't just take 0 to 1, but it also adds this extra phase I to the state. And then you can verify for yourself that Y acting on plus I is I times plus I, and Y acting on for some reason it has now decided to start painting with my fingers. Ugh. Oh man, this is painful. Okay, all right. And Y acting with minus I is minus I times minus I. Now we introduce a gate that has no classical analog, which is the poly Z gate. Again, as we have already seen, we had rotations around the X and Y. So obviously this must be a rotation around the Z axis. But it has no classical gate analog because it doesn't affect 0 and 1, right? The Z gate, because 0 and 1 are along the north and south axis, if I rotate around the north-south axis, I'm not going to change anything about those states. So Z squared, again, of course, is I. but Z acting on 0 is 0. So it looks like an identity gate, but it adds an important thing, this extra phase -1 on the state 1. And that's important because Z acting on plus now will take me from X to -X. That is, so you can see that very quickly. Z acting on plus state on superpositions of 0 and 1, that's when this phase matters. So we see that the action of Z on the basis state will take me to 1 over root 2, 0, minus 1 over root 2, 1. And that is the minus state. And you can similarly verify what the minus state will do. It will go back to the plus state. Okay, so that's the Z gate. And but now we can come up with all kinds of other single qubit gates. So for example, we can define something called the square root of Z. So what is square root of Z? Well, since Z rotates me by 180 degrees in the Bloch sphere, square root of Z, because we can think of square root because it's like an exponentiation or a rotation, square root is just rotating by half the angle. And so this clearly has no classical analog again in our so what it means is that rotating by S squared twice will bring me back a Z gate. So this is now we are starting to see that there are more unique operations that we can do in quantum computing than we could do in classical computing. So the square of S gives me back the Z gate. So again, we can write down the action of S on 0, and now the action of S on 1 gives me a phase I on 1. So now we can ask ourselves, what will S do to the state X? As you can imagine, you can again predict intuitively to yourself, suppose I take a state that's along the X-axis and I rotate it by 90. What do you think will happen? Where will it end up? Anybody?
Plus I.
Yeah, exactly. The Y-axis. So, and we can verify that, or plus I state, exactly. So S acting on the plus state is equal to 1/2 1 over root 2 0 plus I times 1 divided by root 2, which is just simply the plus I state. And S acting on plus I should take us, because it's a 180 rotation around the Z, 90 degree rotation around the Z axis, should take us to minus state. But I'll let you verify that for yourself. Again, as I said, we can continue in this way. T gate is now half of an S gate, right? Or square root of an S gate. Therefore, T squared gives me S, okay? And therefore, again, we can write down T acting on 0 gives me 0. T acting on 1 gives me e to the I pi over 4. Because we just saw that, you know, on the previous slide, S acting on 1 gives me I times 1. I is just e to the I pi over 2. So since T must be now square root of this S gate, therefore it will rotate it by half that angle. Rather than rotating by I, it will rotate by e to the I pi over 4. And okay, I won't go through the math of this, but I encourage you to try and go through the math yourself on what T acting on the plus state will do, T acting on the plus I state will do in this way. Finally, I want to introduce what is probably the most useful and important gate that we will be using again and again in quantum circuits. And this is a very important gate. So please, make sure you understand this one. This is called the Hadamard gate, H, which we'll always usually denote by H. It corresponds now to a 180 degree rotation, but not around the X and Z or Y axes, which are the normal axes that we always consider. But this is around an axis that is 45 degrees rotated from the Z axis and 45 degree rotated from the X axis. So it's exactly halfway in between the Z and the X axis. So it's very weird looking, but its action on qubit states is actually going to be very simple when I write it down in a minute. Once again, h squared, because it's a 180-degree rotation, obviously if I do it twice, I'm going to bring everything back to the way it was. Okay, so that means that h squared will again bring me back the identity gate identity operation. So now h acting on 0 gives me the state plus. I'm defining this. I'm not proving it yet, but we will see in a minute how to prove this. But h acting on the state 0 gives me the state plus, and h acting on the state 1 gives me the state minus. Okay. So now we can ask, what does h do to the plus state? H acting on plus well, that is 1 over root 2, and h acting on 0 gives me the plus state, and h acting on 1 gives me the minus state. Okay, and now to go back to understand what those states are, we'll write plus and minus in terms of 0 and 1. So that's 1 over root 2 times 1 over root 2, 0 plus 1, plus 1 over root 2 times 1 over root 2, 0, oh, sorry, this 1 over root 2 is outside, 0 minus 1. So as you can immediately see from here, only this gives me back the state 0 again. So it's very symmetric, right? So h acting on 0 gave me plus, h acting on plus, no surprise, should give me back 0. Okay, as I said, because it's a 180-degree rotation around that axis. Similarly, h acting on minus, oops. Okay, I mean, I don't need to prove this again, but h acting on minus will give me the state 1. And so on and so forth with plus I and minus I and so on. Well, plus I and minus I is a little bit trickier. So again, I encourage you to work through the math. I mean, it's not super tricky. It's just you just need to follow the algebra and you'll find the answers. And if you have any questions, you can always ask me next class. Okay, finally, I want to talk about general qubit gates. So we have introduced variety of qubit gates, 1 qubit gates, and we can generalize from there. We saw that each of these qubit gates was basically some rotation by some angle. Okay. Now we can introduce, therefore, a rotation by some arbitrary angle, any arbitrary angle. So, and any axis. Okay. So we can take any axis, which I'll denote by the coordinates, or in this case, a vector, nx, ny, and z. And we rotate it by any angle theta. And it turns out that this can be written then in terms of I, X, Y, and Z, meaning the identity operator, the poly X gate, the poly Y gate, and the poly Z gate. This is just a general result that any rotation around any axis can always be written as the rotation around the X, Y, and Z axes in some manner. And this is the result. I'm not proving this result. Okay, this is just the result of the math. So it says that I have to take the cosine of half the angle and multiply the I gate, identity gate, and then I times the sine of the angle or half the angle, and then this general result over here, nx times x plus ny y plus nz z. Again, I'm not proving this. This is a result that comes from quantum physics, so we can't get into it here. But please note that the way I've defined this, nx, ny, nz has to be a unit vector, which means that we must demand that nx squared plus ny squared plus nz squared must add up to be 1. So it's a unit vector. It's a rotation around the unit vector n. So now I told you earlier that the Hadamard gate was a operation that was a 180-degree rotation around the x and z axes. So to prove this, therefore, if I just look at this operation here, I can just put in theta equals 180 degrees, okay, over here, and nx And ny, remember, since it's x plus z, is just 1 and 1. But to be normalized, I need to add a factor of √2. So this is the claim. And so we verify this. So u around that axis that we just talked about. So if you want, we can, I just u acting on any state, well, let's write out u again. So because cosine of 180 divided by 2 is cosine 90 degrees, which is 0. And this sine of 90 degrees is 1. Okay. So for the Hadamard, therefore, we only have this term, which is minus I times e to the I gamma. So this term over here vanishes the first term. We keep the e to the I gamma, we keep the I minus I, and then sine of 90 degrees, as I said, is 1. Sorry, excuse me. And then we keep the rest of this. So the Hadamard, according to this notation here, Hadamard in this notation is minus I e to the I gamma over √2 times x plus z. So you see that we have written it down. Now we need to verify that this indeed does what we claim. That is, that it takes the state 0 to the state plus and the state 1 to the state minus, right? That was how we defined this Hadamard gate over here. If you look back here, this is our definition of the Hadamard gate. So now let's verify that that is indeed the case. So H acting on the state 0 is now minus e to the I gamma over √2 times the Pauli operator, Pauli gate x plus Pauli gate z acting on the state 0. Well, we have already defined the actions of Pauli gate x acting on 0, because x acting on 0 is a 180 degree rotation in the Bloch sphere around the x-axis. So this must be minus e, I forgot the I over here. Minus I e to the I gamma divided by √2. By the way, minus I is of course 1 over I, but okay, that we can get to that in just a second. So this is just the state x acting on 0, x acting on 0 is 1, right? And then the state z acting on 0 is just 0, right? Because z operator is one that rotates around the z-axis, so it doesn't change the state 0. So we end up with minus I e to the I gamma over √2 times 0 plus 1, which of course 0 plus 1 over √2 is the plus state, but now we have this extra global phase minus e to the I gamma over times the state plus. But because gamma was arbitrary, we could choose it in any way we want. We can choose e to the I gamma is equal to I. That is, gamma equals pi over 2. So with this choice, we then are setting the global phase to be gamma. So we must be consistent from now on. We can't change gamma once we have defined it like this. Okay, for the Hadamard gate. We can change it for some other gate. Every gate has its own set of theta, gamma, and nx, ny, nz, basically, is what I'm trying to say. So once I fix it for a given phase, I cannot change it after that. Okay, so for a given operation. So this now gives me 1, and so we get plus. Okay, H now acting on the state 1. So since e to the I gamma is I and minus I, so that's a 1. So we get 1 over √2 times x plus z. Basically, that's what we have defined our Hadamard. And now it's acting on the state 1. So that gives me 1 over √2. Now x acting on the state 1 gives me the state minus 0. Right? And z acting on the state 1 gives me 1. So again, we get now the state minus 1 over √2 times 0 plus 1. 0 minus 1, sorry. So again, up to a global phase, that is the same as the state minus. Okay. Oh, wait. Sorry. X acting on state 1. Let me just make sure. Sorry. Let's go back and look at the definition of X. Sorry. I got to go all the way back. No, X acting on the state 1 must give me back 0. So sorry. So there is no global phase. Okay. Sorry. That makes sense because X squared must be the identity. So anyway, in the next lecture, after we have introduced linear algebra, you'll see an easy way to represent and remember all these things. But for today, I'm doing it by the old-fashioned way again, so that so it must be the Z that is acting on 1 gives me -1. That's where I got the -1 from. Yeah, so that gives me back the state 0 minus 1, which is now just the minus state. Okay, so that's the final result. Okay, and let me, in the very last couple slides, just talk about quantum circuits. Any questions about that, by the way? Let me look in the chat. Are there some? No questions. All right. Okay, so now we can introduce our first simple quantum circuit. That is, any quantum circuit can be written as just a chain of single qubit gates. With 1 qubit, this is all we have access to. That is, we can take the state 0 and we can operate it with single qubit gates like this. And this circuit should be read from left to right. And usually the end, if nothing is given there, it means that a measurement is made. So we measure the qubit and find out what state it's in. Okay. And so this is the first simple quantum circuit. And you can see it's just that. That's it, right? I mean, it looks just like the circuits we wrote for digital binary gate logic, that is classical computing, but now with H and T and S and H and all these different gates that we have introduced in this lecture. Sometimes explicitly the measurement symbol is included by this meter sign. So that's just a different notation or a convention. And so, you should just know that sometimes you might see this symbol here, which just means that we make a measurement. But sometimes the measurement symbol is omitted, but it's implied that you always make a measurement at the end. Okay. So there is a web-based tool, and also later when we see IBM Quantum Composer, you'll see there's a similar tool there as well, which lets you just make as many quantum circuits as you want, and to look at their outputs. So I'll just illustrate that over here. So this is our this is the Quark web-based tool, and the link for it, you just search, you can Google and you'll find it, Quark quantum computing or circuits or whatever. And now here you see, I mean, this has now the ability to simulate more than 1 qubit, but let's just look at 1 qubit because that's the one that we have done so far. So here you can see I'm starting with the state 0, and I can change it to 1 if I want to, but usually the notation is always to start with the state 0. That's the usual convention in quantum circuits. But if you want, you can look at what happens. So this plus symbol, this modulo plus, it looks like the modulo 2 addition. That is the symbol for the binary X gate, for the poly X gate. And we can see why, because 0, when you take 0 and you do it, it's like a NOT gate. It takes you to 1. And you can see what that 1 is. you see here that the block sphere is shown over here. And so it tells you the representation of this operation on the qubit 0 is to take you to the state 1, basically. That means it'll be on at the end of your state. Now, for example, I could follow this state with a Y gate. And now you see that brings me back to 0, as you can see here. No surprise, because a rotation around X took me all the way to the South Pole, and then I rotated by Y. That took me back to the North Pole, just along a different route on the block sphere. Okay, and I can then do a Hadamard, for example, and now as you can see, it took me again from the North Pole down to the equator, because as we know, the Hadamard gate takes 0 and takes it into the plus state, back to the x-axis. Okay, and so this is just a quick way that if you like, and you can also see some other operations, as we'll see very quickly, like a Z and a Y together. That's all like an X gate. Okay, so that the proof of that will have to wait till I introduce linear algebra, but it just says that some of the gates, combinations of them are just equivalent to the other. Okay, and that essentially concludes our lecture. So I'm going to stop the screen share here. Let's see, how do I do that?
Professor,
I'm going to pause and open it up for any other questions that you have about quantum gates and circuits.
I had a question.
Sorry, yes. Can you speak up?
Yeah, sorry. So you say like this is like the old-fashioned way of kind of like running through gates.
I'm sorry, I'm having a hard time hearing you. Let me just try to increase my volume here, maybe. Yeah, go ahead. Say that again. Hello?
Sorry, I was going to type in chat. Can you hear me?
Oh, yeah, I can hear you better now. Yes.
Okay. So you say that this is like the old-fashioned way of like running through like qubit like gates and stuff. How important will it be for us to know this moving forward? Like once we learn a new method of solving like qubit gates.
I mean, the idea of quantum circuits is important, and being able to like work through things quickly on a paper is important, because you don't always want to rely on some web-based tool or some other tool to solve your problem, right? So yeah, so it's important to know it, I guess. I mean, you don't need to memorize which gate is what. I'll give you that, but some gates maybe you have to. It'll hopefully become very obvious their action very quickly as we do more of these examples.
Okay,
does that make sense?
Yeah.
Yeah, I'll give you the numbers, but understanding how to use that and calculate states either by hand, and then eventually by using online simulation tools, yes, but it's always important to verify by hand, in my opinion, at least for simple things. Okay, any other questions? And hopefully the one thing that you should take away is this visual aspect of it, because that way you can even remember the action of the gates even without actually having to memorize anything. Because if I tell you Pauli X gate, you should remember, yes, it's a 180-degree rotation around the block sphere. And from that, you can immediately reconstruct exactly what it does to 0 and 1. And once you know what it does on 0 and 1, since it's a linear operation, you can reconstruct it on any superposition, any of the other basis states. So that, I would say, is very important to remember. Like, X is a 180-degree rotation around X, Y is 180 around Y, Z is 180 around Z, etc. And the exact phases and stuff we'll give you, but it's important to remember that concept. Okay, I'm not hearing any other questions. So there are no more questions. Then have a good weekend, and I will see you all next week.
Thank you.